Hey guys, it's Mrs. Webb here again. I wanted to chat with you guys and carry on with our graphing, our physics graphing for position time and velocity time graphs for uniform motion specifically. And so just to recap briefly with you guys, a couple of things that we chatted about last time were that what this particular position time graph gives us is it gives us the location of the object and the direction of the motion that that object is displacing itself in. So that was the first bit. We can determine where that object is located based on the plot that develops from this position time graph. The second thing was also that from the slope of the lines that we get from this position time graph, we can also determine the speed of that particular object. And when we have these straight lines, when you see straight lines like this and that slope is uniform throughout, that tells us the speed of that object, or that the velocity of that object is going to be constant throughout that entire time segment. And so we chatted a little bit about how that slope will give us the average velocity. And then the final thing we chatted about was how we can also calculate average velocity for an entire trip by figuring out what slope is of the line that connects the initial position to the final position of the trip, right? So this, we can get our average speed, we can get our average velocity from reading our graphs, right? Because we would know the average speed for this would be 20 meters plus 0, and then an additional 50 meters, right? We could figure out for that entire 6-second increment what was the speed versus what is the average velocity for that trip. So what I want to talk about today is you also have to be able to go from a position time graph, and you have to be able to generate a sketch for the velocity time graph that corresponds to this particular position time graph. And you have to be able to go from the velocity time graph to the position time graph as well. And that takes a little bit of practice. But one of the things we did yesterday was we figured out for each of those time increments, what was the slope, right? And so we had figured out that from 0 to 2 seconds, the slope was 0, which meant the object was not moving. From 2 to 3 seconds, we determined the slope to be 20 meters per second to the north. From 3 to 4 seconds, the object was stopped again, and from 4 to 6 seconds, the object was moving at 25 meters per second south. So what we can do from that now is we can generate a graph that corresponds to this particular position time graph. So I've drawn the same position time graph that I had up above here. And like we said, I know from that 0 to 2 second mark, I know the object was not moving. So I'm going to make it smaller just so we can see both of them on the graph on the screen for you guys. I'm going to create a second graph here, and this is my velocity. Notice that I'm saying in meters per second north, so I know that the positive side of this axis is north, the negative side is south. So I know from 0 to 2 seconds the object's not moving, which means that this line, this dark red horizontal line, this is the the velocity of my object at that time. From 2 to 3 seconds, we calculated on our position time graph that the object was moving at a constant velocity of 20 meters per second north. So that means that from 2 to 3 seconds, that horizontal line from the 20 there, that is my velocity of the object at that time. And then from 3 to 4 seconds, it's moving at 0 again. And then from 4 to 6 seconds, we determined that the object was moving at negative 25 meters per second or 25 meters per second south. So this here is the graph that corresponds, the velocity time graph that corresponds to this particular position time graph. Notice that because it's uniform motion, if your position time graph has straight lines, meaning uniform velocity, then the velocity time graph is going to be made up of horizontal lines. And I'm just going to actually draw this in for you just a little bit more so. So this here, these are the lines. You don't need to really put those vertical lines that I attached there, because really the part that's important are these horizontal lines. Now, you can see here that the graph isn't necessarily, it doesn't entirely make sense in terms of a realistic scenario, because you can see that at the 2 seconds, this object instantaneously goes from 0 meters per second to 20 meters per second. That the likelihood of that happening in a real life scenario is pretty much none, because generally there is a time period where the object has to accelerate up to 20 meters per second. But when we're talking uniform motion, we make that assumption that there is an instantaneous jump in velocity, and all of a sudden we're at a uniform velocity of 20 meters per second. Then there's an instantaneous drop in velocity, and then we're at 0 meters per second. Another instantaneous jump in velocity, and we're traveling at 25 meters per second south, and then an instantaneous drop in velocity. Okay, so that's the one thing to kind of remember, put in your study notes. If your PT graph is showing uniform motion, that's going to correlate to horizontal lines for your velocity time graph, because the velocity is constant, right? It's not changing over time, it's continuous. Possible questions here that I was kind of alluding to up above are this. You could be asked, and we've practiced this together, but you can be asked, what is the total distance from the PT graph, right? And total distance would be that distance 1, which is your 0, or yeah, your 10, or your 0 meters per second. Your distance 2 is that 20 meters per second. Distance 3 is 0. Distance 4 is your 50. And again, because it's distance, we don't really care about the directions. We just want to know what's the total amount of ground that that person covered. So in this case, our total distance would be 70 meters. We could be asked, what is the total displacement? Because we're reading, I guess there's 2 ways you could answer this. When we were calculating, we did displacement 1 plus displacement 2 plus displacement 3 plus displacement 4, which is, perfectly fine. Because you've got a graph there, you can also look at displacement final minus displacement initial. And so our displacement final is -20, our displacement initial is +10, which means we've displaced ourselves -30. I mean, you can also just read that from the graph, right? If you're starting here at the 10, you've displaced yourself 10 meters, 20 meters, 30 meters to the south, right? Another thing you could be asked, because we know our total distance and our total displacement, we can be asked your average speed and your average velocity, right? So our average speed is 70 meters over 6 seconds, which is 11.7 meters per second. Our average velocity is -30 meters over 6 seconds, or 5 meters per second. So that's kind of all the different types of questions you can be asked for. Another thing you could be asked for is to, instead of going from the position time graph to the velocity time graph, you could go the reverse way. Okay, so things to keep track of are that in a position time graph, your slope is going to give you the velocity of the object. In a velocity time graph, the slope does give us something very important. Actually, I can't remember if I have it down here for you. I don't think I do. Let's actually right now, just for interest's sake, let's figure out what the slope of a velocity time graph gives us. So we know that the slope, we know that the slope, if we look at it in terms of units, is our rise over our run. Our rise, again, in terms of units, is meters per second. Our run is seconds. And so this is the same as saying meters per seconds times 1 over seconds, which gives us meters per second squared. And this, you may recognize, is our unit for acceleration. So your slope of your VT graph gives you the acceleration, which actually, you might think makes sense, because if your velocity is here at a constant of -10 meters per second, you're not accelerating, right? You know that you're not accelerating. You're traveling at cruise control, right? You're continually over time traveling at the exact same speed. So it makes sense that the acceleration be 0. The other thing we can figure out is we can figure out what is the area underneath this particular velocity time graph. So remember, slope gives you an important variable in physics underneath the line. Slope of the line gives us an important variable in physics. Equation of the line can give us an important formula in physics. Area under the curve can also give us important details in physics. And if we calculate the area under this curve, we know the area for a square or rectangle is base times height. Well, let's look at it in terms of units. Our base here is, base up here is our seconds. Our height, which is our y-axis, is our meters per second. So if we say base times height, base times meters per second, those seconds cancel out and we're left with meters. Well, you guys know that meters is a distance, right? So area under the curve for a velocity time graph tells us the displacement of that particular object. And so if we were going to go from a velocity time graph here, and actually the other thing is, let me put this in terms of a formula that we can get here, right? Because area under the curve will give us an important formula. So we know base is our change in time here. We know our height is our velocity, so time times velocity. And we know that if we multiply these two things together, we're going to get our displacement. So that's our displacement. If we rearrange these variables, we get average velocity is equal to total displacement over total time. So the area under the curve of a velocity time graph gives us our formula for uniform accelerated motion. So exciting. Graphs actually tell us really important stuff, hey? The other thing to be very, very aware of when you're going from a velocity time graph to a displacement time graph or a position time graph is that the velocity time graph, it tells us nothing about where the object is starting from. So we can't get that reference point from the VT graph. The question would have to say the object starts at 0 or what have you. There's no way for us to figure out here where that object started on our graph. And so if we go back here, let me show you what I mean. Okay, if we know that the object is traveling at 0 meters per second, and we know that there is no area under this line because it's on top of that x-axis. We know that the object has displaced itself 0 meters, but we don't know 0 meters from where, right? This could be 0 meters from the 0 on the y-axis. It could be 0 meters from the 20 on the y-axis. It could be 0 meters from the -10 on the y-axis. We don't know where that starting point is. So there's nothing from this line that is indicating to me that the object started at +10 meters per second. That would have to be given to you in order for you to know where to start your graph. And if it wasn't given to you, then you could just start your graph at the 0 because we don't know exactly where it's starting. So if we're going from here, we know that this original position here has no area under the curve, so that means that it's displaced itself 0. Well, the question here isn't telling me anything about where this object is starting, so we're just going to start at the 0, just to keep things simple. We're going to start right here at the 0. We know the object doesn't displace itself for the first second, because I'm reading that here from my velocity time graph. In this second segment between 2 and 3 seconds, I know that the base is 2 seconds. The height is 10, so I know that the object displaces itself 30 meters, but I'm just wondering here why. Oh yeah, 2 seconds and 10. My multiplication was bad. So we know that the object, it moves 2 seconds and it has a height of negative 10 meters per second. So it's displaced itself negative 20 meters or 20 meters to the west, because here they're telling me that velocity is in meters per second east. That's the positive. So from 1 to 3 seconds, it displaces itself negative 20 meters to the west. So there's my second data point. I'm connecting those two dots. In this third segment, from 3 to 4 seconds, there is no displacement. So that's my next segment. And then from this last segment, we know that the base is 1 second. The height is 5 meters per second. So it's displaced itself positive 5 meters. So that means that from this location, I'm going to travel 5 meters in the positive direction, okay, which puts me at the negative 15 mark. That's where I finish. So this would be the displacement time graph for this particular VT graph. And we have to be able to go back and forth. So we're going to give that a lot of practice during class time to make sure you guys are okay. I've got one more example for you guys down here. This one is a displacement time graph, and we want to draw our velocity time graph. So we calculate our slope from this segment here. Our slope here is 20 meters per second, which means that our velocity is continuously, for that first 1 second, 20 meters per second. Then the object instantaneously goes to 0 meters per second. So I'm showing my VT here at the 0. From 2 to 4 seconds, my slope for this object is 15 meters per second north. So I draw my 15 meters per second over that time increment. And then from this section here to here, we need to look at it, or we calculate the slope, sorry. So from here to here, if we calculate our slope, we're getting 20 meters per second south the entire way. And so here we drop to 20 meters per second south. Okay. And that's about it, guys. We're just going to give that a lot of practice. It's it is more challenging than to do than may meet the eye. There's a lot of stuff to keep track of, but we'll give it some practice during class time. As always, if you guys have questions, please jot them down, bring them to class. We'll talk about them when we see each other. But for now, I hope you guys are doing well. Stay healthy, and we will chat soon.